Hello guys, my name is Spyros Zigouris. I'm an informatics professor. This is my YouTube channel and you are on videolearner.com. Today we're gonna complete our courses about IP datagram structure fields, and we're going to see an example about IP datagram fragmentation, or as we say, IP packet fragmentation. So let's go to the next field. Next field is the protocol field. The 8-bit protocol field contains a numeric value which indicates the transport layer protocol to which the data contained in the packet belongs. This informs the IP protocol at the opposite end, at the destination computer, for example, of which transport layer protocol to deliver the data to TCP, to UDP, or elsewhere. For example, we have here the transport layer, so we have our TCP or UDP protocol. If you have access to a computer with Unix or Linux OS, in the /etc/protocols file, you can see the matching of numbers and protocols for that field. The same thing with the Windows OS computer. We have system root, system 32 drivers, etc. protocols. Now, the next field, the 16-bit header checksum, ensures the integrity of the header field's values, applies only to the IP packet header, only in the header, while the field itself is not involved in the calculation, assuming it contains the value 0. So we need to have a value 0 here in header checksum, because header checksum protects against data corruption, and it should be 0 if there is no corruption. Now, the integrity check of the header is considered essential, as when passing the packet to several routers, they modify the header fields, which increase the probability of errors. This is why we say about corruption. Let's go to the next option field now, which is optional and is used for special functions, but not often. When available, the padding field fills the option field with zeros, so that the header as well is an integer of 32-bit word. Here it is, we have 8-bit, 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 octet, 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 octet. And now we are done with IP datagram fields. So let's have a look in example of datagram packet segmentation. An IP datagram packet coming from a token ring network is to be forwarded to the destination computer, which is on an Ethernet network. These two networks are connected to an IP router in the token ring network. In the second level, the MTU, maximum transmission unit, is 4,482 bytes. That is, the frame can transfer data of maximum size of 4,482 bytes. Now, just remember that maximum transmission unit, that is the maximum data length of a packet called frame in the second level of a model. Here it is in data link. So we have packet called frame. Here is a frame, and then bits in physical layer. Now on the other side, the Ethernet network has an MTU of 1,500 bytes, which means it can transfer a maximum of 1,500 bytes. The data of a token ring frame, which is an IP packet, does not fit into an Ethernet frame. Therefore, the IP packet must be split. This allowed if don't fragment flag is 0. Describe the process of fragmentation and reassembly of the original IP packet. So we have fragmentation and reassembly. So the original packet in token ring has a total length of 4,482 bytes, or a header of 20 bytes. So we have data of 4,462 bytes. Here it is, we have in token an MTU of 4,482 bytes. Here it is, 20 bytes IP header and data of 4,462 bytes. So we have fragments. Each fragment should have total length, including header, less than 1,500 bytes. And the data length to be an integer multiple of 8. So the first fragment, it will be k times 8. So it will be multiple of 8 data length, and the same for the second fragment, and so on. To get the value of relative position, we mean fragment offset of the segment. So in the Ethernet network now, the actual intended message, that's to say data with no header, clear data, or else we can say payload length, is equal to function of integer, and in the brackets we have MTU minus 4 times IHL divided by 8. So we have integer 1500 minus 20 divided by 8. So we have 185 octets, or 185 times 8 bytes. So payload length, clear data, is equal to 1480 bytes. The original packet of 4462 bytes of data will be split into a number of fragments. Okay, with this arithmetic operation as follows, we can find the number is integer clear data of the first original packet divided by clear data of the second packet plus 1 packet. So we can find integer, this operation is 3 plus 1, so we have 4 packets. 3 packets of 1480 bytes and 1 with the remaining data, that's to say 4462 minus 3 times 1480 bytes, so we have 22 bytes of data. So first fragment, second fragment, third fragment, and the remaining with 22 bytes of data. Next, the figure below shows the fragmentation process. We have the original packet with header and data, first fragment, second fragment, third, and the last one. It is the fragmentation process. Now the fragment offset, or the relative position of each fragment in bytes, is calculated as follows. We have fragment offset is equal to n times integer, and in brackets we have MTU minus 4 times IHL, and all of it divided by 8. This is clear data. So we have n times integer 1480 divided by 8. So we have n times 185. For n we have values from 0 for the first fragment, 1 for the second, 2 for the third, and so on. So we have for the first fragment, fragment offset is always 0 with MF1. For the second fragment, fragment offset is 1 times 185, so we have 185 fragment offset with MF1. For the third fragment, fragment offset is 2 times 185, so we have 370 with MF1. And for the fourth fragment, we have offset 3 times 185, so we have 555 with MF0, because it is the last fragment and there is no more fragments. So we have more fragment 0. The relative position of the fragment allows the destination computer to place the fragments in the correct order to reassemble the original packet, even if they have reached the destination in a different order. All fragments of the same original packet have the same value in the identification field, which is the identity of the packet. As you can see here, some information about all fragments. For example, we have IHL header value of 5 for all fragments. That is to say, we have 5 words of 32 bits. This is words, how many words in header. Total length is 1500 for all fragments except the last one, which has the value of 42. For data, we have total length minus 20, which is header. So we have 1480, except the last one. We have 42 minus 20, so we have 22 for data. Identification, we have the same for all fragments, because from the original, we have the same ID. Don't fragment flag, we have all zeros. more fragment flag, we have 1, 1, 1 and 0 at the last one, and fragment offset, we have these values. While the fragments reach the destination computer, they are reassembled in the original split packet. So we have these fragments and we have reassembly, and we make the first original packet. And that's it. We completed the ipDataframpt structure, and we made an example from Spyro Ziguris, our YouTube channel, and videolearn.com. Bye bye.